Yo, yo, yo. What's up, everybody? Welcome back. Today, we are working on making a virtual PCI device and a driver to go with it. So, the intent of this is that we've been kind of working a little bit on like demystifying the Linux graphics stack. So, last stream, we kind of worked on uh, trying to draw something to the screen using direct Linux APIs. So take out OpenGL, take out Vulkan, no graphics API. Just like how do I like get a handle to pixels on the screen and draw them? And this is part of a investigation on if we were to build a graphics card ourselves, like make a graphics card in FPGA and use it to do something interesting, what would that look like, right? And uh, in order to figure out what like a good design for that would be, we should try to understand what's actually going on when we use graphics cards for real, right? So that's kind of like the project we're working on. And today's topic is an attempt to get closer to understanding how we would implement a graphics driver ourselves. So we're taking the idea that like your GPU is typically a PCI card. Like not all GPUs are, right? Like everything in your phone, saying like typical GPU is maybe not quite right because like, every single ARM Android phone probably has a GPU inside it that's not PCI. But for our case, right, the GPUs that we'll be playing with will be, right? So the thought is if we make a PCI driver with a custom PCI device to go with it, we will be able to then extend that in the future to have some form of PCI API that will allow us to render something 3D accelerated on the host through some form of API into a virtual machine. That's kind of what we're working on. And so today's topic is essentially just let's get a PCI device up and running to play with. So I'm thinking like a good initial target would be like to model it as like an LED, right? So if you look at like your computer, maybe we'll draw a picture because we haven't been very visual yet. You have like your computer, right? And these stupid little blocks, like whatever. And like on the front of this thing, you have like a hard drive LED, right? And like this thing will like flash orange or something when your drive is running. And maybe you have like a power button on here as well. If I remember correctly, these things are exposed in Linux as like sys class LEDs, right? So here I just have like a list of LEDs that I could write stuff on, right? And this is like a generic Linux API, and so I'm kind of thinking what we could do is we could kind of make a fake network card, or not network card, sorry, a fake like just a PCI card, so like PCI card, and we'll like kind of pretend that on him he's just got like some big LED, like some like big multicolored LED on here, right? Maybe we can like render this LED like in the browser or something. And then the thought is we'll like make this GPU device, we'll hack it into qemu so that we have like a PCI card to play with. And then we will write a driver for this thing that controls the LED through the sys class LEDs interface. Seems pretty straightforward. I think that should be doable within one stream, and will set us up so that in the future we can like actually implement like a DRM thing on top of that. I was considering just to guard against why didn't you do this? I considered looking at like a shared memory approach. So there's like an existing qemu device called IV Shmem, which allows you to basically take a like a file descriptor on the host and use it as backing memory in a PCI device in the guest already. The reason I didn't want to take this approach is because it feels like it's kind of limited in that you can only do what the existing driver allows you to do. And I don't think that's what I want to do. Maybe it is, but I don't think it is. So I would like to write my own PCI card so that we can kind of like configure it the way we want to. In the past, we wrote a really, really bare bones shitty operating system, right? And in that shitty operating system, we had to implement PCI support in order to get networking. So we played with this RTL 8139 card, which has a implementation in qemu, which is really good for us. But I was like refreshing my memory on this morning, and my if I remember correctly, what happens here is you write into like they have this concept of like registers, and so the registers are like a specially memory mapped section of that the PCI that like when you write to those addresses, it just actually goes and sends PCI commands to that specific PCI card. to write specific numbers to specific locations. And so like you in here, one of the things that they do is you say like, okay, I'm going to give you like a real address in physical memory that you can like transmit from. And then I will trigger you to actually do that write out with a command. And so in my mind, probably a graphics card in the future will look something like this. I mean, I could be wrong. Like we have a sample size of one PCI device, and so like maybe other PCI devices look different. We've only ever looked at one before, as far as I remember. But it seems like a reasonable approach, right? Where you're like, imagine you want to like upload some vertices to a GPU for rendering later, right? You could imagine that you give a chunk of host memory, and you say, please take this chunk of memory and put it in a GPU buffer with this idea, right? You could imagine that that is an API you could have. And in that case, the idea of having like a register that you write to that says, boom, start transfer with this address and this type seems like a reasonable API. So I think that we're going to follow this behavior in some form of way. I'm kind of imagining that maybe we will start with, we probably might skip the memory transfer part for today because I think that's too hard. But I think that maybe we will start with the idea of registers, and maybe we'll have like a red register, a green register, and a blue register, and we'll put those together to light up an LED. That's kind of what I'm thinking. So plan of action: make the virtual device in qemu. Make a virtual device, not a complicated one, not finish it, but make like just anything that we can like access. Then we can like write like a stub driver in Linux so that we can like poke and prod it and see what we can do. And then read and write some value to that host memory through to that virtual PCI device, and then use that as a way to like set parameters for some LEDs, hook it up to the LED subsystem, and then maybe we'll like bang out a visualizer on the host side. That is what I am thinking. That's what I'm thinking. So let's jump in and see what happens. I will admit I did make a very, very simple qemu device before stream because I was not sure that I understood how it worked. So we have a little bit of, I cheated a little bit, a small amount, just to make sure that like we wouldn't get stuck in the first 5 minutes of stream for 2 hours like we have done in the past. So let's take a look-skis. So if we are to look at maybe, we have like 2 reference drivers that we know that we kind of want to look at, right? There's IV shmem, which we know is like a way of like having like a memory mapped file over PCI. And then I think the other one that's probably good to look at is the RTL8139 driver, right? These can be our 2 references. And the way these things work, as far as I can understand, is they have this like runtime inheritance model. So I was looking at like docs, fuck off. Oh my god, stop. How do I get out? Oh, I'm gonna fucking lose my mind. Dude, what is happening? It's mad because the tree sitter Python thing is like crashing. Oh my god. Okay. TS install Python. Like, get out of my fucking. What a bad API. What a bad user experience. Holy. Okay, but we'll try. We'll look again. So docs. Quam RST, here we go. So this is the Q object model documentation. And this kind of explains like how to set up a device. But being stuck and figuring stuff out is just the fun part, Mick. Yeah, I know, but I wanted to do the getting stuck on the fun part, not on the boring part. Anyways, so they have this class system where they have like what is effectively runtime types hand implemented in C. So you kind of like make these class types that are different from like instantiated types. So there's kind of like meta object information that you put in the class type, and then there's like an instantiation of the actual type here, right? So you have my device class will instantiate a thing of many instances of my device, and the my device class here they're just kind of mirroring an existing class. But you can set all sorts of like parameters on that thing. So if we look at the RTL8139 example, they have like a RTL8139 class that inherits from a PCI class. And when we want to like get information about this class, we call class init. And this class init function, no client attached. Hold on. Let's get into an environment. qemu shell. let's get into on environment so that we can jump to definition, because that will be very useful. Very, very useful. Where were we? So source qemu, and we're looking at RTL 8139. Yeah, so when you go to RTL class init, this sets up like some important attributes about like PCI device, right? So here they say PCI match me against like this vendor ID and this device ID. This is part of the PCI class information, right? And this is shared between all instances of this thing. Then they set up like callbacks and stuff. So they say like, okay, so for all instances of RTL 8139 classes, when we initialize them, we're going to call this initialize function. Shit like that. And then I think that's kind of the main piece here. The other main piece is the inheritance model is very. I was surprised this is legal, to be honest. But what they do is, you know, instead of like in C++, you do like class A inherits from B, right? And you know, then you have like class B, and B has some function. I don't know, like do stuff, right? Whatever, and then you can like implement do stuff in A, right? You do like equals 0 in this language or something. What they do here to implement that, we've kind of seen like multiple approaches to this in the past that I've been kind of more familiar with. One of these is like you do struct A in C. Struct A has a member B, and you can by passing around pointers to B, if you know that that you are the implementation of A, right? So if you have like you know, you have void do stuff like this, right? You can. Is this how you write this? I think it is. I think this is right. Void, maybe you have to write in here. There we go. That looks more reasonable. That looks more correct. What you do is, I guess this actually would typically take in a struct B star B, right? What you would do is in your implementation of A, you would assign this to a function that's like function void do stuff struct A star A B star B. And in here, you can get a little crazy and you can be like get A from B, because now you know that you are in the this is A do stuff, sorry. That you will know that you are the concurrent implementation A, and you can be like, well, my pointer B is like the first thing in A, so or the second thing, right? Say it's like the second thing. You can be like, well, I know this is going to be 4 bytes offset from A, and so I can kind of like use offset of and subtract 4 to get there. That's one way of doing this. The other way of doing this is, sorry, I think I got this a little bit wrong. It's usually like this. The function pointer goes in here. Sorry. The other way of doing this, we've seen it often, is that you have like user data like here, right? And you then pass in the user data to this callback, or you like get A by basically casting the user data, right? You say like struct A star is B user data, right? This is another way to like extract A from a thing. But this is not what they do in qemu. They do neither of these things. What they do is they just do this. And instead of doing some sort of like container of, they just do this, where they say, okay, well, because we know B is the first element in A, we just fucking cast it. And I was like, that's legal? But it turns out the C spec has a special casting rule. So usually you can't just like cast pointers of arbitrary types to other arbitrary points. But if they are the first member of a struct, that's legal. I didn't know that until yesterday when I was like, what the fuck? That's how they do this? So their inheritance mechanism is like, in my opinion, fucked. But I guess legal. I don't like this. I don't like this at all. Because like it kind of forces you to have like single inheritance only, which I guess is like maybe good in some way. It just feels dirty. It feels dirty to just cast pointers of one thing to another thing, you know? But maybe it's just because I'm less familiar with it. Anyways, that's how their object model works. But they have all this metadata to go with it. So what was it? We were looking at docs q object model RST. But anyways, in here they have an example on how to make the world's simplest device. So maybe we start by copy pasting this and we put it somewhere. So if we look at like where the vshmem thing is, this is in hardware music. So we can do like hardware music sphero dot, oh fuck. We'll call it hardware music sphero.c, because We don't have a better name for it. Oh fuck, what did I paste? He didn't like that. Oh god, I probably pasted something that wasn't what I meant to, and now my whole terminal's frozen. That's super cool. I don't like that at all. Can we just kill Alacrity? Oh, that sucks. That's a first. I think I've never done that before. Okay. Whatever the fuck we just did was stupid, but we can fix it. We can fix it. So we were copy pasting from Q object model RST. We were copying their example to here. Boom. And now we have to compile this thing. So I was looking for, well, what if we just grepped for ivshmem.c? Surely the build system must do that somewhere. Right? And so in here, they have config ivshmem device. If that's true, we compile this thing. So it's like, okay, I guess we'll do that. Right? I guess. And I guess we will probably say if we have a Sphero device, we want to do that. And if you grep for config ivshmem device, or maybe just ivshmem device, here we go. You start to see, oh, kconfig. This looks familiar. This is like the kernel build system. So it looks like we can just kind of probably specify that we have a Sphero device that defaults to compiled if we have PCI devices. We don't depend on this. I don't know what MSI non-broken is, but we probably don't depend on that. And I don't think we even depend on Linux, right? I think that we are just kind of chill if we have a PCI device. And so if we are lucky now, we can go into our build directory, and hopefully when we build, we will see that our file is built. And maybe it makes sense for us to just like at the top, right, like error, we are in sphero.c. And this will be a good indicator that we have in fact hooked up to the build system correctly. That would be a good indicator. So he's reconfiguring himself. My suspicion here is that the entire build depends on kconfig. So if you reset up kconfig, it has to recompile like half the world. Because when I was experimenting with this earlier today, I saw maybe like 1,000 files compiled here out of like the 9,000 of qemu. So not everything, maybe like all MISIC hardware devices or something. But we will see. Yeah, 2,000. But we will live. This doesn't take too long. And so we can just wait, watch him whip, and watch him nay. Is that Will Smith's daughter who whips and nays? Silento. Okay. What year is this from? 2014? Holy shit, I'm old. I kind of thought this was like recent, but that's 10 years ago. That's crazy. All right. We're maybe halfway, but hopefully the rest of the files are fast to compile, because C is pretty fast to compile. It's not like C++ with 1,000 files. No, she whips her hair back and forth. Oh, is that different? Whip my hair back and forth. Oh, that is a different thing. Dude, can you imagine if your name's Will, naming your kid Willow? That's crazy, right? Just being like, you know what I want my kid's name to be? My name. Like, come on. You'd have to be so unoriginal to not be like, what if we gave her her own new name? Okay, yeah. So error, we are in sphero.c, so we are chilling. We've hooked up to the build system. And let's just kind of keep going a little bit. So here he's complaining that the example code that we copy pasted from their docs is not good, which is pretty shit, but we'll live. I think what we should do instead is we can maybe copy paste the includes from another file and just kind of run with it. And then we can be like, first of all, he's complaining about like unused includes, so we definitely don't need zlib, right? I don't know why he's bitching about that. And we can just kind of like delete all of this stuff, I guess, that's unused, except that apparently it is used just through transitive dependencies. Yeah, so net is pulling in I usually don't really think we're using this either. Type device. So we could look for like, where's type device defined? This is in qdev core. So maybe we pull that in. I guess we probably want the PCI device as well, which we don't have here. So in RTL 8139, we are going to want a PCI device. So that's probably coming from this include here. And then can we delete the rest? That looks like it's good. Okay, let's replace everything that says my device with Sphero. And this is going to be, I guess, my device gets replaced with Sphero. Okay. And let's see, like, what is this thing doing? What is this thing doing? Is it normal that I don't understand anything? I don't understand anything either. So we're kind of like two peas in a pod, two corn on a cob, if you will. Can we maybe check that, like, can we make sure that like only one thing compiles? I guess we'll just wait it out. We're gonna have to compile the whole executable at some point. But likely if this succeeded, then we got past the fact that our thing wasn't compiling. Okay, so if I understood all the like code we were grepping in happy hour yesterday, if I understand correctly, this device registration code actually gets kind of crazy. So the qemu command line arguments will walk all elements that have a parent of type device, if I remember correctly. And so that's why this like weird like runtime type info is like really useful. We don't need to relink everything. We can get rid of just like x80 qemu system x86 64 is all we really need here. All we really need here. So if I remember correctly, the qemu command line will actually walk every single device. And so just by doing this, we should be able to run qemu system x86 64 device Sphero help. Device Sphero not found. So I'm full of shit. It's because type Sphero is called my device here. What if we write Sphero here, like we intended, like God intended? Device Sphero help. So there are no options for Sphero, but this is an indicator that he did in fact find that Sphero exists, which is very cool. Very, very cool. Very cool. So what is happening here? There are macros around, if I remember correctly, that kind of assume that there is I don't really know what this type def is for. I bet you could get rid of this type def and everything would still work. But we'll leave it in for now because we are going to turn this into a PCI device, I think. Maybe. Yeah, is that the easiest way forward? It would be nice to. What's like the easiest way for us to prove that we have done something correctly? I think probably if we make a PCI device, run the virtual machine, and look at ls PCI, we want to see our PCI device in there. I think that's probably like a good initial step. So maybe we look at like the RTL 8139 example that we've been looking at, and we can see, okay, so his type info says, I inherit from PCI device. So let's do that. And then this kind of here is kind of claim, if we inherit from PCI device, like I was saying before, where we cast our state to just be like the first element, I believe that this means that our parent object has to be a PCI device as well. If we look at like the RTL 8139, somewhere they define object declare simple. Maybe we'll actually do this. Object declare simple. This declares, I think that this declares all of the class stuff for us so that we can kind of like get away with it. There's a bunch of like macros in here that I don't really fully understand. But I think if we just take this and we throw it into Sphero like this, boom. This is going to take in Sphero state and Sphero, I believe is how this works. I don't really know, but we will figure it out. I think that this works. I think. And then here we were going to look at the RTL 8139 state has a parent object PCI device. So we should probably copy that. And then we can compile and see if it still works. If we compile, we're probably chilling. But I guess since this is like kind of like runtime inheritance, like runtime class information, we might be missing some stuff in here for sure. So he is asserting that we are conventional PCI device or CXL failed. So this is in PCI.C 2647. Oops. Hardware PCI.C 2647. So here he is trying to check if we have interface conventional, interface PCIe, or interface CXL. He's saying, are we one of these things? And so presumably the RTL 8139 specifies one of those. Okay, so we have interfaces that says I am one of these. And if I remember correctly from reading through the Q object model docs, I think that they say something about this stuff. Interfaces allow a limited form of multiple inheritance. Instances are similar to normal types, except for the fact that they only define their classes and never carry any state. As a consequence, a pointer to an interface instance should always be of incomplete type in order to be sure it cannot be dereferenced. That is, you should define the type def struct something IF so that you can pass around something IF star SI arguments, but not define a struct something IF. The only things you can validly do with the something IF star are pass it as an argument to a method on its corresponding class, or dynamically cast it to an object that implements the interface. So can we look at like an interface info? Like, what is this thing? This thing is just a name. So we just say, hey, we have a name for this thing. And hopefully that gets us past the compiler. Or the runtime error, I guess. qemu? Okay, so this is good. Our options now have a bunch of PCI related shit on them, which kind of indicates that we've done something right. However, I feel like I'm not ready to run this thing. Isn't it fun how every large C project implements its own little language on top of C? Yeah. It's kind of fucked, huh? Kind of fucked. But it is what it is, I guess. I will say I'm not the biggest fan of this object model so far, but maybe it's just because I'm unfamiliar. But we will see. So maybe let's look at these guys' initializer. In here, they set the vendor ID and the device ID. I feel like that's what I want to do to prove that this is working correctly, right? If we set our vendor ID and device ID so that when we do like ls PCI-v, hold on. Run. And we go to our console. We want it so when we do ls PCI-v, we see something in here that looks like something that we made, right? That would be a really good start for us. And so I think probably setting the vendor and device IDs are probably the pieces. And so I think we will create a class init function. Boom. And we will make a Sphero class init. And we will copy whatever the fuck this thing does here. So do we have to go in order? Probably, right? This thing needs to be defined above because C languages are single pass or something. They go top to bottom. We'll name this Sphero class init. And so this guy is doing that like bullshit casting, right? So our PCI device is both a device class and a PCI device class. And these macros, I was looking at these yesterday, kind of eventually just get into this static inline class type. No, this declares class checkers. Oh, sorry. So PCI device class is a function. Hold on. PCI device here. It gets a class type PCI device class. He's claiming that he's defined it within this macro somehow. So this is obj name here, where obj name comes from PCI device. So that's not it. Define class checkers. Here we go. So here he defines a function object name underscore class that calls object class check on this thing, which calls a dynamic cast thing where I'm pretty sure that this returns an object class, which is a top level thing, and then just casts it to the PCI class. Right? So that's what I was saying earlier, where they just fucking like hard cast shit. So probably if you look at PCI device class, he has his first element is device class, and the device's first element is object class. So we can go the other way where we get an object class and we just like fucking cast that bad boy into both of these things, and both of them are fine. Might be interesting to see those macros expanded with -e or whatever the flag is. Yeah, that would be. Can we do that easily? Could we do that easily? Probably. Yeah, probably we can look at compile commands JSON and look for sphero.c. And then we could try to run this command. In the correct directory, which is this directory. So we can like, Jesus Christ, that's a long command. And then just, can we do, instead of creating an object file, can we just do -e? No input files. I fucked up. Because we do still need the input file. That's true. So we just delete the, oh god, oh god. Delete the output file. And then can we do like -e? Less? And look for PCI device. Oh, we just look probably from the bottom. Here, this calls PCI device class a function. And this thing is defined here. Right? So this calls a function that takes in a void star, returns a PCI device class cast of. This isn't very nice. This is not very helpful to look at all. Anyways, we have a class here, and let's set the vendor ID on this thing. And these things, let's look at the RTL 8139 example again, and let's just like look at what are these things. These are hexadecimal numbers. So here we can probably just be like, and set the device ID to and then hopefully if we did this right, then we will see within the virtual machine. That's what I'm hoping. Oh god. Ninja, what was it? qemu system x86-64. And let's, I guess, add this device to our little run command. So can we just do like device sphero? And is that all we need? Maybe. So here we see which is sick for us. That's pretty cool. So we have a PCI device. It does, nothing, right? But at the very least, it exists, which is pretty cool. What language is this? This is C, but it's like really fucked up kind of meta languages, like meta programming on top of the language C, for qemu. Okay, so I think the next thing I want to do here is, before we start getting crazy, let me think for a second. I think that I want to make a driver that instantiates itself when it sees this thing in the Linux kernel. I think that's the next step. Because once we have that, then we can start poking and prodding this thing a little bit more in like a more advanced way. But I don't really know how to like access. I guess we could look at like sys bus PCI devices, and we could look at ours. And is there like something that we could like get from here that is kind of interesting? I think I've seen that you can get like access to the ROM, like the bar information from these, where bar is like in the PCI header, there's like stuff, right? And from from the RTL 8139 example that we have, when we implemented this like a year ago in our operating system, I believe that it was that the bar was memory mapped in as like for like register access. Fuck it. Let's just make the driver. We'll just make a driver. That's probably the way to go. That's the way to go. Okay, so I unfortunately need to have two different shell environments for qemu and Linux development right now, because when I tried to merge them into one, there were like conflicts for multiple types. So let's kind of just switch environments and get into Linux. And I think we know Linux uses kconfig, and so we probably have like a similar thing. Let's look at like RTL 8139. Where does this like live? They have a driver at drivers.net Ethernet Realtek. If we want to make it like an LED driver, we could maybe look at like drivers. Is there like drivers LED? Oh, there is. And it looks like there's like some that are backed by GPIOs, right? I see LED's GPIO here. I see Blink M. I see like a bunch of words. But I think like the way that the things are generally set up is that the driver lives where you expect its functionality to be, not its bus. Like it's not based off like you don't have like drivers PCI all your PCI devices, right? We have like I think I was looking at the Blink M driver earlier. Right, this is an I2C driver, but it lives in the LEDs folder. So maybe we can have drivers LEDs sphero.c. And I was looking before stream at the documentation for PCI LEDs. I was looking at the LEDs index here, and I was looking at here's like I just saw LEDs Blink M, so that's why I picked that one, is because I've seen this word at the top of a list. So I'm okay with kind of using LEDs Blink M as a little bit of a example, but this is going to be for the LED side. So maybe we want to start with looking at the RTL 8139 again as an example for the PCI side. Nice. Okay. So the way these like Linux drivers work is you define like a function that's like, I am a PCI driver, right? And then you give it like an initialize function, and he gets called with an already initialized PCI device. And the way this works is like this macro, if I remember correctly, expands into like, put this thing in this special section of the binary. And the Linux kernel walks all of these things. And so I think that there's like somewhere, he like knows that he's a PCI driver somehow. Register PCI driver. This is like a function that runs. So here, right, so on initialization, he runs this function which calls register PCI driver, and then then that like registers him with the PCI subsystem or something like that. So what we should be able to do, I guess there's probably also documentation PCI index probably. Is there like PCI RST, structured PCI drivers? This is a lot of words. I don't really want to read this at all. So I think we're just gonna go by example. We'll go by example because I think I understand well enough. So we should be able to slap a driver in here. We'll call this Sphero driver like this. And I guess he has a DRV name here, so we will kind of copy that behavior and we'll call this Sphero. He has an ID table. So this is how the PCI subsystem knows to instantiate this driver. So that like a we put in before, he's going to like look for a PCI device that matches that specific ID, because those IDs are supposed to be unique per PCI card. And so we can be like, okay, we are a driver that is valid for anything that is like, well, hold on. Let's see how these things are defined. They have PCI device, vendor Realtek, and ID Realtek. So can we just be like Sphero and Sphero, and then be like okay. And then here we can say we match against things that are Sphero and Sphero. All right. And it looks like probably you put like a null device at the end to indicate the end of the list would be my guess here. Okay. We want this to be like PCI table, I guess. We will call it this. And then we will make a probe function that we call as well. So this, if we hook everything up right, this will get called when we boot up, and we should be able to see that we have like some indication of something happening. And so here we will just do nothing, and we will just be like printf yo 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 what's up, what's up, what's up. Except it's not printf here, it's printk. And then I think you might have to specify a like level here, but that's okay. We need some includes here, so let's kind of like Linux module sounds promising. Probably Linux PCI also sounds interesting. And then probably like print K needs to come from somewhere. Although it doesn't. Okay, he's mad at Sphero probe, and then we just won't do this stuff. And this needs to be Sphero driver. But it looks like everything in here is not mad according to Clang tooling, which is a good starting point for us. What if there is more than one driver for a given PCI device? The first one registered wins. We could look. So who is going to iterate these things? Probably like drivers PCI PCI.c would be my guess, and we're gonna look for ID table in here. No. Who iterates the ID table? Probe ROMs doesn't look like what we want. A lot of these are assignments. I wish I could see like only calls. PCI match ID. Oh, this is like a Quarks thing though. Oh, this isn't like a fucking called thing though. That's okay. Okay, so probe ROMs is one usage. One is PCI driver.c. This looks promising. Oh, we were already here. So maybe these get stored somewhere. IDs go to. I guess we could look for like a PCI probe, right? We should look for who probes this thing, and that'll give us a better clue. So if derv probe PCI match device, PCI device probe. Okay. So here we have PCI device probe. He's going to probably, but he's like, I am just a device. And then in here, he matches the device to an ID and then calls probe with that ID. So matches the device to an ID. Also, here we already know what driver we are though. To PCI driver dev driver. So here the PCI driver has already been picked. So the PCI bus must choose here. Okay, I don't want to figure this out. I don't want to figure this out. I suspect that it's just like there's some ordering somewhere. But I think it's going to be a little hard to track down. Right, because probably the bus is responsible for like matching the device in some way. So here he does like, oh, bus match. Wait. PCI bus match. So he figures out which driver here. So tell if a PCI device structure has a matching PCI device ID structure. Used by driver to check whether a PCI device present in the system is in its list of supported devices. Returns a matching PCI device ID structure. If it, okay, so here he goes. So this must be called with like every driver or something. Driver match device. Driver attach. Try to bind a driver to devices. Okay, wait. Okay, yeah. So here the driver is attached, and when the driver is attached, he looks for all elements that might be reasonable for him. And then eventually that gets back into probe. So I guess it's probably set by it probably binds to the first driver that matches it, where driver order I think is not super well defined, but if you had them as like external kernel modules, would be whichever one you loaded first. I've also seen that there's like blacklists and stuff that you can set. But I don't know. Who knows? Not me. You fucking nerd sniped me and distracted me from the the real unimportant work of continuing on here. So let's add our driver to the build system. So we can probably assume that there's like a make file in here. And in here we're gonna have a similar thing where their build system is going to depend on kconfig. So in here we can probably just kind of say config LEDs Sphero, I think is probably reasonable here. Oh, geez. I hope you guys didn't hear me burping the mic. That was gross. And can we do LEDs Sphero.o? Looks like what they want here. Which kind of indicates to me that we named our file wrong, probably. It was drivers, LEDs. Everything else is prefixed with LEDs. So let's also prefix our thing with LEDs just to fit in, right? We want to be cool. And so we will try our best. And then we were going to look at LEDs kconfig, and he is going to define like, we're going to have config LEDs Sphero. And I guess tri-state is probably like we can be on, off, or a module. We don't depend on LEDs class, but we do depend on PCI probably. And we're not going to have any help because we don't need help. And we're going to call this LED support for what's it called? Sphero LEDs. Okay. So now let's see if we can get our thing to build. So I think we can do the same trick we did earlier, where we intentionally fail compilation here. And that way we can prove to ourselves that we hooked it up right. You just call himself it. It's been done in the past. I can't remember if I did it just now, but you know, I could have. So hopefully if I search for Sphero in here, we do see us, and we want to compile it directly into the kernel, probably. I guess we could compile it as a module, but whatever. And if we make now, hopefully we see a build error on Sphero LEDs Sphero.c. Why is he building so much shit? I guess maybe we haven't built our kernel for a bit, or maybe that somehow triggered some sort of like major recompilation, but that's okay. He identifies as LED. What's the problem? Yeah, I'm an LED. Blink, blink. Luckily, the kernel build does not take that long. This is not as consequential as when we've deleted our Qt build directories in the past or our build root build directories. This should be done relatively quickly. Relatively. But we'll give him a second anyways. We didn't delete. You did though. Just saying. Okay, it's a group effort. Okay, you guys and me are the same in this world. I've actually gotten into the habit for a long time of saying we whenever I talk about any code at work, whether or not it's mine, because that way I can, if I say it's stupid that we do this, that's a lot better than saying at work it's stupid that so and so did this, and also that way like I can also shift responsibility from myself onto other people, right? I can be like, we do this when really it's like, I did that. It's kind of like a mask for both if I'm shitting on someone or shitting on me. I get to mask both of those things by just saying we. And so it's leaked into my everyday life. This is actually taking longer than I thought it would. I wonder if I accidentally copied in a different config. I mean, he is building x64, so I think we're fine. It would maybe be interesting to copy build Linux config to kernel config here and just make sure that like our diff isn't like, oh fuck. Oh no, our kernel config isn't here. Fuck. Okay, I know why. I was building in the source directory instead of the build directory, so I actually wasn't using the previous build config. I was just using the wrong shit. Oopsies. Oopsies. Let's face it, if it gets merged by the team, it's a we problem. That's my argument, yeah. Okay. Let's try this again. This should be much, much faster. And now we can make sure that the only thing that's changed now is config LED Sphero. And we do see an error here, fail to compile Sphero LEDs. So we're like kind of like double winning there. Double win for us. So let's take out this intentional build error and try building again. Okay. Kernel builds. Huge for us. And oh, maybe not. Oh, what is that doing? Oh, he's building some modules as well. Sure. And we're just going to pre-jack this run.sh so we can get there quick. He's compressing himself. Little gzip, and let's fucking see what we get. Root. Oops, I spelled root wrong. Can we just scroll up in this window? Oh, hell yeah. Do we have a yo, what's up? Let's go, dude. Okay, so that's really good. That means that we have like successfully found our PCI device, and we have like at least have a driver that is like here. He does something. Now, I think the next thing to do is to try to hook up some bars. We're gonna write some bars, where bar stands for something region, base address region. So the pattern that I saw when we were working on the RTL 8139 is that the bar can define either an IO space address or a memory space address, right? So if I remember correctly, there's like CPU, and the CPU talks to like memory controller that talks to RAM. If I remember correctly from a long time ago, there is a shared thing. These like lines that are used to talk to the memory controller are also on this like IO bus. And if you are trying to talk to stuff that's on the IO bus, this means that all memory accesses can't be happening anymore, right? You can't use the memory bus while you're using the IO bus. I don't know if that's really effectively a problem, right? You kind of like a multiplexer here or something, right? I don't know how much of like a real problem that is, because I guess really you can probably only get one thing from memory at a time anyways. But my intuition and what I've read online is that like it's preferable, like if you kind of have this, right, where you have like PCI device here, the PCI can be talked to either through the memory controller or through the IO controller. And like the PCI can specify, I have IO address this or memory address, like if this is X and Y, I have like memory address X, IO address Y. You can specify either. And I think you're supposed to prefer this. And if I remember correctly, the RTL8139 has both options. So we can, I don't know if I saw that defined anywhere here, but I was looking through my code. Where did I see this? Maybe in the datasheet for this thing. I saw like bar. Oh yeah, it was definitely in the datasheet. Hold on. I know where it was. It was in PCI configuration space registers. Fuck. Can we copy paste this? Or we'll just go to page 36, I guess. What page is this? How can we tell? 15. We got to keep going. 36. Here we go. So this is the configuration table. So every PCI device has like a fixed address, I think. I can't quite remember, where you talk to it by specifying this like specific address through like something like this, where you say, I want like, I have on PCI bus 0, I have the first card. The first card might be both like a GPU and something else. So you have like a function associated with that thing. If I remember correctly, you have 256 bytes of stuff that you can do by just kind of doing IO reads and writes to this specific place. And so here, this is telling us what is in those specific places, i.e. the vendor ID, the device ID. But in here, they talk about it offset 10, they have an IO address, and 14, they have a memory address, which lines up with a 10 and 14 here. Address 10 and 14. Now, in here, they're saying IO bars or memory bars. And if I remember correctly, you can flag if you are a memory bar or an address IO bar with bit 0 of this thing. So that's kind of a lot of shit to say, like, the RTL8139, which we're using as our reference, supports both of these mechanisms. And what you are supposed to do is you're supposed to look up one of these, who cares which one, and say, I want to map this memory somehow. And so in the RTL8139 Linux driver, I was looking at this pre-stream, and I'm pretty sure they use the memory mapped one. So they do something like, in here I saw, let's see, he initializes, he sets some stuff, PCI enable device, request regions. No, not quite what I'm looking for. Oh, here we go. PCI adder is PCI resource slot start from number 1. So this guy indexes into the resources that are available at the given index. So this is 1 in, which matches up with this data sheet of the bar 0 is IO, bar 1 is memory, right? And then when we look at usage of this thing, he remaps this thing into registers. Registers get set into CP regs. And if we look for usages of CP regs, we see them calling things like copy word 32 to CP regs with write L, where write L is defined as a build MMIO write. So they do like a move L to this thing. So they're not doing in and out, which are like using the IO bus. They're doing move, which is an instruction to write to a specific location in memory, right? That's what we are seeing here, which means that this is all of the understanding lines up here to say that they are looking at bar 1, which is a memory mapped resource, and they are reading and writing to things in that memory map resources for configuration. So we can do something similar. We just have to set up a memory mapped bar and do stuff with it, right? So we can go back into qemu land, I think is probably where we want to start here. Back into qemu land, which means that we have to go back to our qemu environment. Nix shell qemu shell, and we'll do the same over here. Maybe I should have 2 tabs open so that I don't have to keep flipping back and forth, but shut the fuck up. Okay, let's go back into qemu. And let's look for RTL8139.c, and we can look for like examples of how they set themselves up. So this is class initialization. Instance initialization is probably more what we want. No. Oh, this is a class instance. Maybe we want in their class init, do they set up a probe function? Yes. Okay. So this is where they do the actual work of setting up their device. And here we see that they are setting up a bar for I/O and a bar for memory at different indexes. Do we know what indexes they're at? Oh, here they register them at locations 0 and 1. Okay, so here I guess what they have done here is they have set up an I/O region with I/O operations. So on like register write, if they get a write L, they like write to some specific register. Okay. So we can kind of define functions that do whatever the fuck we want at writes to this bar. What is bar? It's a memory region. And I was looking at memory RST, I think. And we should probably read a little bit of this because a memory region is confusing. I've seen it used for like several things in the qemu source code. So the memory API models the memory and I/O buses and controllers of qemu machine. It attempts to allow modeling of ordinary RAM, memory mapped I/O, memory controllers that can dynamically reroute physical memory regions to different destinations. The memory model provides support for tracking RAM changes by the guest, setting up coalesced memory for the KVM, blah, 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 who cares? Memory is labeled as an acyclic graph of memory region objects. Sinks, leaves are RAM and MMIO regions. I don't know what MMIO is. Memory mapped I/O, that makes sense. While other nodes represent buses, memory controllers, and memory regions that have been rerouted. Sure. So like that aliased memory section would be one of those reroutes where he's going from like memory address to go to this I/O region instead, please. Okay, is there anything super interesting here? Okay, how do we like initialize stuff here? A RAM region is simply a range of host memory that can be available to the guest. You typically initialize these with memory region init RAM. Okay, some special purposes require variants of resizable RAM, blah, blah, blah. I feel like that's not really what we want, right? Because we want to like, we don't want just like a range of host memory. We probably want to like do actions on these things, right? When somebody writes to us, we want to probably, I'm imagining we'll probably write out to some file that is served somewhere else. Like we'll want to process the latest LED state and write it out to disk somewhere instead of trying to integrate with like QEMU's graphic system because that will be too hard. Raw read-only memory looks like RAM memory, but and forbids writes. Okay, ROM device works like RAM reads directly, but like MMIO for writes. Invoking a callback. I guess I kind of want MMIO, right? A range of guest memory that is implemented by host callbacks. This is what I want. So you initialize these with memory region init IO, passing it an ops structure. So it looks like if we wanted to do like memory mapped IO, we just do this and then register it at a bar like this. That's kind of my guess. That's my guess. So can we kind of start there? So let's, I guess we'll kind of copy paste like this section of code and kind of assume that the rest isn't important. A good assumption for us. And we'll do this. And we know that we probably want our device. So Sphero state is a Sphero of dev. Okay, so that works. I don't think we actually care about device state right now. And who cares about setting up configuration? We don't. That's for sure. And S is here. This is us. This is us. So if he had bar IO in RTL 8139, we can just kind of, wherever the fuck we were just now, here, slap this here. Is it defined? It looks like it is. And then we can do bar IO. What is the second parameter here? Object owner. Oh, so that's me. Okay, sure. So I go like, I have a memory region. We'll just call this bar for now. Actually, we don't have like multiple bars to worry about. We have to pass in some operations, which are going to be memory region ops. So I guess we kind of yoinkies this guy. And we say, what? We have our operations. So struct sphero ops. And we're going, no, it's not a struct. Sorry. We have static const memory region ops sphero ops like this. And here we are going to implement, maybe we will just only implement write for now. We'll kind of start there and we'll kind of figure out the rest as we go. So let's do like, how do you do this in this language? I've dot write equals, here we go. And this will just be a function pointer to like some function we implement up here. So we'll call this a sphero write here. Boom. Right. And for now, we'll do nothing, and he will take in sphero write. And maybe we'll do something. Maybe we will print. So I guess the first parameter here is probably my device, I would assume. We could look at their ops structure. They have a opaque pointer that is converted to their state. Yeah, so this is us. This is me. So we have, I guess we can ignore that, but it's valid for us to cast that. And can we just say like, printf wrote to, probably this is like lu. Yeah. Lu with lu. Yeah. And this is going to be adder data size. Boom. Okay. No previous prototype. Oh, so he wants this always to be defined, I guess. Oh, unless I write static, probably. Nice. All right, so when we get constructed, we are going to be like, yo, send me this shit. Okay, and then S, whoa. Oh, so the owner and the opaque pointer, I see. So here we give this as an owner type, and then this is how we define what gets put into our callback. Here we're going to call this sphero, I assume. So this is, yeah, but the name, I guess, and the size. So the name, used for debugging, not visible to user ABI, and size is just the size of the region. Okay, so let's say that we have maybe 32 bytes, right? Fuck it. Print K, buddy boy. Actually, I'm pretty sure it's printf here. Printf here, because we are in qemu virtual machine user space, not kernel space, you know? And then we will register this thing as a memory space thing at bar 0. And then we'll be like, yo, realize is sphero realize. Boom. Oh yeah. So I guess here, let's also just say like, hi mom, I'm a PCI device. Let's just make sure that we see something. And let's go into qemu build, cd build qemu, and build this thing. Let's build it. Long unsigned. Oh, he just wanted %u, not lu. I'm surprised. U here. Oh, just the last one? Oh, because the size, I thought the size was also uint64. I'm so used to sizes being uint64s. But I guess they are not in this case. All right, so let's run this shit. And we do see, hi mom, I'm a PCI device, which is super cool. And I would like to see if we can write to the bar somehow. And I think we can probably do it without doing driver shit, because I think I've seen, if we go to like sys bus PCI, devices, and we go to our thing. I think we see resource 0 now. Oh, but I guess I can't just like echo shit into that. You kind of need to have like a specific right with size. So I think we pivot back to driver world. Let's get out of this window. Who fucking cares about this? Did you figure out why clearing the CRTC wasn't working? No, I just left that as an unknown. I was like, maybe someday we'll understand. But for now, I just wanted to move on a little bit. All right. Kernel development time. We go back and we will try to write to that thing. So I think that we are going to copy the RTL 8139, whatever the fuck, driver a little bit to try to figure out how to map the region. And then we'll kind of move on from there. So in RTL 8139, we saw they extract the thing from the bar. Well, I guess let's kind of like look at what they do kind of on initialization in general. So, right, this seems important. Enabling the device, right? I don't know what set MWI does. Memory write invalidate PCI transaction. Ooh, what does that mean? What does that mean? Memory write invalidate. What does this do? Okay, so this says like he writes a word to the config space of the PCI device. So that looks like we should see that in like our configuration space table. So he writes it to PCI command number 4 here. Okay. So what does that mean? MWI command register. I think I saw it here, command register. Memory write and invalidate enable. If set to 1, the device can generate memory write and invalidate command. Otherwise, the memory write command must be used. What does it mean? What does it mean? I want to know if we need it. Request regions, reserve PCI IO and memory resources. So we probably need this. Probably. And then do they like unmap this stuff on remove? They do release the regions and clear MWI and disable the device and stuff. Okay. So I wonder if they're like devm handles for this. That'd be kind of cool. That would be very cool. So let's go to what am I looking for? Sphero. So let's do, at the very least, enable device. And what would be cool is there a devm PCI enable device? Damn, would have been cool. Would have been cool. But oh well. So I guess here I like the idea of error out free. What does he do in his error out? Yeah, so we do need to disable the device if we fail. That's a good point. But here we don't really have that. So I guess we'll have like int rc. Is that what this returns? Int? Yep. And we'll do if not rc. I guess we just return. I guess go to error seems reasonable. That feels reasonable to me because like I guess like because if we're copy pasting or we put more code above, this will become like, you know, this is more copy pastable. It's almost as if they assume people know what they're doing. Yeah. And we don't know what we're doing, and that's okay. So I'm not going to set MWI because I don't know what it does. But I think requesting regions sounds important to me. And we're going to go error out, go to error regions, and error regions is going to delete PCI device. Okay. Then we ask for the PCI resource start at position 0, where I assume that this gives us like a resource size t. Okay, and is this a type def? Yeah, it is. Okay. If not RC should be if RC. Yeah, that's true. That's true. Thank you. And then we have an address to map. And so I think that they do like IO remap here. Where IO remap is, I don't really know. Let's take a little peeksies. IO remap performs a platform-specific sequence of operations to make bus memory CPU accessible via read, write, row functions, and the other MMIO helpers. The return address is not guaranteed to be usable directly as a virtual address. Okay. I mean, that sounds important. That sounds important. And this is going to return a what? Void star. I guess for us, we're going to treat these as uint32s, probably. We'll just have like a few of them. And what did we say the size was again on the other side? We said 32, right? We said 32 bytes in the qemu side. 32, yeah. So we will have 32 bytes of registers. And then I assume that we need to put those in some structure somewhere, right? That's what he does. Then he does a bunch of other stuff that I don't really care about. Then he has driver data set. Okay. Hold on. What's dev here? Dev is a net device. Does he have like his own structure here, or is he kind of stashing everything in the net device? He has CP. So CP is his internal structure, and he sets that probably on the net device. Yeah. Okay. So in our case, I guess we're going to have a struct sphero priv, right? And inside we're going to have uint32 star regs. That's our only thing. And then we will say that we have our struct sphero priv is equal to nothing, where you put a 0 in here or something to 0 initialize it, and then you have priv regs equal regs. Okay. I guess we probably have to allocate this stuff, right? Surely this has to not live on the stack. In which case we probably need to do like a kalloc. This guy does alloc ether dev, but under the hood this probably does some sort of like kz alloc feels like what I'm used to seeing. So we'll say struct sphero priv star priv is equal to this. We are looking for struct size. Why does this exist? Calculate the size of a structure with trailing flexible array. We don't need that. So we're just going to do size of sphero priv. And what is kernel account? I'm used to GFP kernel. What does kernel account do? GFP account is the same as GFP kernel, except allocation is accounted to kmem cg. What the fuck is that? What the fuck does that mean? I assume that we don't need that, because I don't know what it is. So can we just do GFP kernel like this? And then we need to set, I guess if we error out here, we're going to say, I guess we don't really have anything that could error out after, but we would have to free this memory if we wanted to. So maybe we'll call this error device, and we'll call this error all. And then here we can still write k-free. In fact, whoa, no. What am I doing? Fuck this shit. Fuck this shit. Have you guys heard of devm? I'm a big fan of devm. This is like, you can tie the allocation to the lifetime of the driver, and then you don't have to think about it. Right? You can do devm kz alloc, and we can attach it to the lifetime of our pdev dev. And then we do the rest of the stuff. So then I don't have to worry about freeing. Dev size GFP. So this is just kind of the same thing right here. And so what happens here is when the device goes out of scope, it will walk everything that has been allocated with dev malloc and free it itself, which is pretty cool. Pretty cool. And then I don't have to think about it. So this is, I guess this goes here. Yeah. Yeah. Okay. Okay. So then let's just start by like write L 5 to the address. Right, so on initialization, we should see in qemu, it should print us, hey, he wrote the number 5. I think. Oopsies, what the fuck am I doing? Build Linux make-j9. All right. Give him a sec. He's thinking. He's gonna re-zip the whole kernel and shit. All right, run. This is already running, so I guess we close it. Obs, thanks for the prime. Much appreciated. Okay. So did we see? Oh, wrote to address 0 with 5, 4. So 5 is probably the value and 4 is the number of bytes, if I remember correctly. Yeah, look at that. Guys, we're so chilling. We are so chilling. Okay, so let's make it so that, okay, read, write, value to host. So we've written a value. I guess let's read a value back as well. Okay. So how do we want to hold this stuff? I guess we will hold the value in our memory, right? So we'll have like, if we're trying to make an LED, we'll make a multicolor LED. So let's just do like int32t r, g, and b. Okay. And we will make it so that switch on adder, right? If we get 0, we write to r. Case 0, sorry, I forgot this language. We'll do, here we'll do like, sphero state star s is equal to sphero opaque. Okay, then we will be like sr is equal to data. Case 4, we write to green, and case 8, we write to blue. Which means that we probably didn't need 32 bytes of address space. But you know, whatever. And really, int32s is stupid. Right? These should be... That's fine. We'll do int32s for now, just because we're choosing to use write L. No, we'll do U8s. But I'm worried about like non 4-byte aligned writes. I seem to remember seeing something about that in the PCI stuff. Right? Like, I guess it doesn't matter. We'll do it this way for now. We'll do it this way for now. We don't have to get too crazy. Okay, so on read, we are going to have another function. So this is the function sphero read. He is going to call sphero. Maybe these macros are not right, by the way. I think we're not supposed to use this macro here. I think we're just supposed to cast it. So I think we're just supposed to do this. Because we're not doing like any inheritance here. We're just like using classic void stars. You know? So here we'll switch again. Here we forgot to add some breaks. We always forget to break. And this is going to look very similar. I guess we'll have like a default as well. Which is not valid here. So default we will maybe just return. here we will return maybe like a sentinel value of like bitwise not of 0. Will this do what I want? Like, does this know that this is going to sign extend to full U64? Or is this language one of those shitty languages where this is always an int and this will just not return, this will return like 4 bytes of f's instead of 8 bytes of f's? I actually can't remember. But I guess there's only one way to find out, and it is never triggering it and never thinking about it again. We actually don't even have to figure it out. I want it though. Like this. So uint 64t x is equal to not 0, and then can we do like let me think. Maybe fuck. I just closed. You know what? Why don't we just use our compiler? I don't know why we're doing this somewhere else. Int main void. Uint 64t, which comes from std_def. X is equal to not 0. Then we do printf %l x, I guess. Include std_int maybe is where it comes from, and then include stdio. gcc-o test test.c test. So this is 1, 2, 3, 4, 5, 6, 7, 8. So I guess we're chilling. It's funny that I don't know that off the top of my head though. Maybe I should be less shit. Okay. Now what? I guess these all get turned into returns. So here we'll do return. Boom, boom. Cool. And now this must get passed into read as equals Pharaoh read. My man, if you're shit, there's no hope for the rest of us. My friends say I have this really bad habit of when I play video games with them, and no matter what the scenario is, I tell them, oh my god, I'm so sorry, I'm shit. Right? And because in my mind, it's like, I should have been able to 1v3 them, right? And it's my fault that we lost that because it's expected that you guys die, is kind of like the implicit message there. But, and then he's like, that's actually like a really like rude fucking thing to say. I'm like, yeah, that's kind of true. But there's like a part of me where it's like, you kind of like normalize. I'm not trying to make a statement that's saying I am better at coding than you. I think if you are saying that about yourself, then you believe that, right? But like, I think you kind of like normalize, like humans in general, normalize whatever their expectations are to like what is around them. And so in my mind, when I'm like, I'm just like, I made a mistake. And it's a mistake that I feel like I shouldn't have made. And I just like have like these standards for myself. And like, so shit is not like, when I say like I'm shit, I'm not trying to say like there's no objective measure attached to that. It's more just like a discontinuity between what I expect myself to do and what I actually did. You know? You know? It's also not very serious. Anyways. No previous prototype, so this needs to be static. And then what? Then what? I guess we're probably chilling. So we can maybe flip back into driver mode. I guess let's build this. Ninja this thing. And then we'll go back onto the driver side. And let's like then read. Like we'll write 5, 6, and 7 to regs plus 1 plus 2 because regs is a uint32, so these will get aligned by 4 bytes. And then can we read them back? You know, just kind of be like boom, boom, boom. And let's just see that we got the right things back. So I'll be like int r, int g, int b. Wow. And it'll be like got %d, %d, %d. All right. All right. So if everything is good, we should just see 5, 6, 7 there. And if we do something stupid, then we won't see 5, 6, 7. Okay. Got 5, 6, 7. Look at us go, baby. Look at us go. Look at us go. So I think that means we have done a successful read and write. Let's hook up to the LED subsystem. Let's hook up to the LED subsystem. So, what does that look like? We had blink M here, and they are an I2C driver, right? And on their probe, they must attach to the LED subsystem. LED class dev register sounds like the right thing. Register a new object of LED class. And we pass in the parent structure, so a struct device, and then a cdev, class dev structure for this device. So where does they make that thing? Here they, oh, this thing has like many LEDs, it looks like. So, and it looks like the usage of this thing is they use the container of style. They use the containers of style. So if they're using container of, that means that we store LED class dev in our structure, like this. Which means that we need probably the LED subsystem in here. Boom. Okay. And when we have our callbacks, we construct some callbacks that will write back, that will like extract our register value somehow. So we're gonna have like a cdev to Sphero, I guess. We'll copy that. And this is just going to be Sphero priv, and the device is, we left it named as LED cdev, so we're chilling there. We are going to construct one of these, I guess, down here. How do they? Oh, I guess there's no construct, there's no like allocation. We just need to initialize that thing. So I'm assuming that there's some sort of like functions that this guy wants to implement, right? Certainly there is some sort of thing that he wants to do. So class dev register. Somewhere he must be, oh, here. Brightness set blocking. Okay. So what do we, is it only brightness? Do I not have the option to do like a multicolored LED? I thought they did, but maybe not. Maybe we specify red, green, and blue as separate LEDs. That might be how it works. Linux LED RGB. Okay, that's not what I want. I want like sys class. Color. LED device name is device name, color, function. Okay, so if we look at like ls_sys class LEDs, we have like, we have multiple things like on my keyboard. I have numlock and scroll lock. But if these were multicolored, then I might have like input color numlock. I see. What is in like XPad? Yeah, okay, so they just have brightness. Okay, so I guess theoretically, if we wanted an RGB light, we would register 3 class devs, right? That's kind of what this is indicating. So we'll have this like R cdev, R cdev, G cdev and b, right? And we are going to be like, I guess we'll use the container of macro manually ourselves. I'm fine with that. And how do we do this now? So we have a name. So our name, they said it should be our cdev name is going to be Sphero red, right? Or something like this. Examples of proper LED names. And then I saw something about like LED color ID definitions from the common.h. Although this is a device tree, but that's fine. So it was this Linux DT, no? DT bindings, LEDs common.h is kind of what they're kind of saying that we should do. These color IDs are numbers. Is this? So if these are numbers, how is that this? You know? I'm just going to type the letters red. I'm okay with that. Who cares? Who cares? So we'll just do, green and blue. We don't have to be too crazy. We don't have to be too crazy. Status yellow / brightness, status green / brightness. Yeah. Okay. Then we also probably have to set their callbacks. So brightness set blocking. And I guess we want to set the max brightness to, maybe we'll set that to 255 for now, even though we're using UN32s. I feel like that's stupid. And then we'll have the brightness set blocking. And he is going to be like Sphero red set, I guess. This will be Sphero blue set. And this will be, G, B, B, which means that this should be R, he should be here, this should be G, and this should say green. Okay. What is the API for this thing? Here we go. So this is going to be, what is it, Sphero red set? Interesting. Is it? Do I not have like a? I thought that I could specify like a integer value. I thought. Pattern set, brightness set. We now support variable maximum brightness. That's what I thought. So how come these are fucked? Oh, maybe there's I'm confused. I'm confused. Are there like newer versions? Check if LED driver supports blah blah blah. Is there like some other version that we can look at? Doc LED index RST. LEDs class multicolor. Okay, wait, okay. This looks more like what I want. So how do we set this up? Multi-files. Okay, okay. So LED brightness, the brightness level for each LED is calculated based on the color LED setting divided by the global max brightness setting multiplied by the request brightness. This seems like too much work. Too much work. I more want to know how the fuck do I register a function that has like a variable brightness? Am I stupid? Must not sleep. Use brightness set blocking that can sleep while setting brightness. Okay. But then, like, is this enum LED brightness just like a fucking lie? It does kind of look like it, huh? Right? Like, can this just be any value? Is this one of those like fucked enums? Could be. We could try. Maybe we just assume like value. He does just cast it to a U8, which is very funny. Okay, that's confusing, but we will live, I guess. So we'll just do container of led cdev. We want this is a container. We are trying to map it to struct sphero priv, which hasn't been defined yet, and our member variable is our cdev. So we'll kind of put this down here, and then we'll say, struct sphero priv star s is equal to this, and then we should just be able to do. Do we return 0 from this? I don't know. What do you do in this other thing? Does he? I assume 0. I assume it's like yeah. He's returning. Yeah, return 0. Okay, seems reasonable. So then we can just do s regs write l u8 value. Do you like something like this? No. Write L. Am I stupid? Unsigned int. Oh, it's the val first? Okay. Okay. And then we do the same thing for green. And the same thing for blue. We have to be careful here because we've written the rcdev here and here. But otherwise, I think we're chilling. I think. In which case, if we, no, I guess we also have to register these things. So we have to do, what was it? How do we register these things? It's led dev class register. Okay. So RC is equal to pdev dev. We are registering ourselves. No. Yes. Yes. And we are registering with priv rcdev. And fix me free because I don't want to deal with this right now. And error check. But sometimes you just cheat a little bit. And now this stuff should get exposed to user space, I think. Maybe. We'll find out. We'll find out. All right, all right, all right. We'll run it. So now, cd sys class LEDs. Okay, so we go sphero blue. Brightness is 0, and if we, I guess we probably have to initialize it with the value we read initially. But then otherwise we can like echo 55 brightness. And I don't see any logs. Oh, we don't log from here anymore, which is a little annoying. It's hard to know if it's working correctly. It's hard to know. But that's okay. That's okay. Okay, so we have our RGB lights. We have our RGB lights. And what would be cool is if we could like visualize them somehow. So what I'm considering, I think the easiest way to do this is probably to make a little shitty web server that just like feeds a file. We'll just like spit out the red, green, and blue values into files as text. And then we will serve those files and display like a shitty little SVG in the browser that's like the light, we'll make a little circle that's like the right color. That's kind of what I'm thinking. That's what I'm thinking. So if we did here on right, we go like right out right LED values. Okay. Okay, yeah. And he is going to come from sphero state. And he's just going to be like, I guess here, maybe we'll have like FD. Which means that on initialization, we could make this a parameter, but I don't want to. We'll just be like file star f is equal to, I guess, sf is equal to f open of like, you know, data dot JSON. Sure. And here we go like, what's the arguments to f open? Is it characters or hello, f open car star. So here we do like RW. Probably just W. Probably just W. And then do we need to like truncate as well? Man 2 F open, man 3 F open, truncate. Truncate to 0 on W. Okay, so we're chilling. We're chilling. Okay, then on right, we can just be like f printf, you know, R is going to be a number. G is going to be a number. And B is going to be a number. Yeah. Yeah. Okay. And then we need to do like fsync. No. How do we like flush this? Is it with a new line? And then we probably want to like fseek from the beginning. Seek set probably. So this is like seek set. Boom. Can we like truncate the file automatically? Is that something we can do? F truncate file star. How to truncate files. Blah, 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 blah. Oh my god. Oh my god. libc set truncate file after write. F truncate sounds right. Oh, ch size as well. Oh, there's Windows. Yeah, okay. But like, these aren't with like file star API. I guess we will just reopen the file every time, and then that will kind of auto truncate it. But weird. Weird. Good enough for me. Good enough for me. Okay. Let's build and run again. Build and run again. And then we can go into like here. And go Sphero blue, echo 5 brightness. And then we should see data JSON 567. Oh, I guess. Oh, wait, hold on. 565. Let's go. So here we can say 255 brightness. And we are chilling. We are chilling. So let's do the quickest and dirtiest thing we can think of, which is maybe HTTP server, Python HTTP server serving some SVG that is generated automatically. I guess we could just generate the SVG. Yeah, maybe we just generate the SVG, huh? So can we do like SVG circle? How do I make one of these? Like examples. I want like the dumbest example I can think of. Maybe SVG tutorial, introduction. Fuck off. Getting started. There we go. This is what we're looking for. So we want a circle that is filled with a specific color. So we'll do like 100 by 100, center 50, 50, and a radius of 50 as well. So if we do like xvg open test svg or Firefox test svg, there we go, nice little green circle, and then we could do like svg color RGB. Deny. Fill hash value. Okay, cool. So we just gonna yoinkies this, slap it in some quotes. Here we replace every quote with an escape quote. No? There we go. Okay. Then why is he still mad here? Missing, terminating, character. Do I need to do like this? Oh, I do. All right. All right. And then here we just make this %o2x, %o2x, %o2x with a little hash symbol in front of it. And we will write this to test SVG. Okay, let's start there. Let's start there. Let's start there. Whoa, why? Oh, because I need to limit it to only building one thing. Okay, doke. So now if we go into here, we go to sys class LEDs, and we go to sphero blue, and we echo 255 into brightness. Then we go over here and we refresh. No bueno, because it is not here anymore. It is here. Oh, okay, blue. And we go into sphero green. And we echo 255 brightness and we refresh. Oh, dude, that's kind of sick. That's kind of sick. All right, all right. The last piece here is a shitty piece of JavaScript to refresh this thing. So can we like HTML? So I guess we leave like index HTML, and he's gonna be like doc type HTML. No, doc type HTML. I can't remember how to do this. HTML. What do they do? Doc type. It's a like this, and then we do HTML. HTML. There's a meta refresh you can do IRC. Oh, I can do it in HTML. Okay, okay. HTML auto refresh. Nice. Does this go in the header? Yeah, it does. So here I can just do like every second refresh, and then I can do like body. And can we just like include the SVG image HTML SVG image? I can't remember if there's like special rules for this. I seem to remember having issues with this on the QR code shit, but I think that it looks like it's fine. Oh, I think that was because the SVG itself included more PNGs. But this should be fine. Do I need to do a closing tag here? No. All right. So if we go here, we go to index HTML, and he is refreshing now, which means that somewhere else we should just be able to run our thing. This is somewhat a waste of time, I understand, but it's fun to get like a finished thing that we can look at. So can we like go to LEDs and echo 255 to star sphero star brightness? I guess that he doesn't like that. Echo 255 brightness. Wow. Wow! Look at us go! Hooray! That's kind of fun. Kind of fun. Obviously, this doesn't matter, right? Obviously, this doesn't matter. But it's kind of fun. It's kind of fun anyways. Because now we have, at the very least, information now in our brains about how to implement both LED stuff as well as a PCI. We've like made a PCI device in qemu. We have what else have we done? Made a PCI device in qemu. We've written a PCI driver. We've hooked up some LEDs. So like we've kind of covered a lot today with this silly little toy, and it should set us up so that in the future we are kind of better positioned to work with like DRM stuff, right? Because now that we have a PCI device and a PCI driver, who's to say what we were going to do with it? This is just a quick little fun example. So happy with that. Happy with that. Thank you for watching, guys. This is a almost perfectly 2-hour stream. We actually almost hit it on the dot, which is pretty sick. So thank you for watching. If you liked what you saw, we stream most days at around 12:30 to 4 o'clock Pacific time. Today we skipped the 12:30 to 2 segment and just did the 2 to 4 segment because I sometimes need to prepare a little bit more in advance for a stream to work well. But generally we have 12:30 to 2 happy hour, 2 to 4 normal stream. So if you are watching on YouTube, you will be watching the main stream, and if you want to see happy hours, you should swing by on Twitch, which will be linked in the description, or check out the Patreon and YouTube member archives. otherwise, this code should end up on GitHub eventually. I don't really know where I want to put it yet, but I imagine it's going to end up in this GPU testing environment GitHub repo probably. So if you want to check that out, you can swing back by in like a few days. What else? Like, subscribe, Twitch Prime, and I think that's it. No more plugging. Goodbye, YouTube and Twitch. Let's raid someone.